So let's start. The next speaker is Kareen Rozen from Brown University. She will speak on bad repetition. Kareen, you have 45 minutes.
Thank you, Yael. This is also a joint paper with Geoffroy de Clepel. So this paper is an experimental study of repeated games, but perhaps going against the grain, one that examines the prevalence of bad outcomes rather than good outcomes. As we all are aware, the folk theorems in repeated games mean that there's a lot of possible equilibria, and this is often presented as good news. So for example, you can sustain cooperation in the prisoner's dilemma. And there is a large experimental literature in repeated games that examines the determinants of such cooperation. One thing to keep in mind is that if a player can certainly secure their Nash equilibrium payoff, or the min-max utility coincides with that, you can only improve people's welfare by repeating if repeating has some impact. We think that there's also some important settings where the min-max is worse than the stage Nash. In that case, you could have strategic considerations that lead people to take actions that are detrimental for themselves and others, and the outcomes could be worse than repetition of one stage Nash. Now, whether this actually happens in practice and what causes that to occur, these are empirical questions, and then we're going to try to study somewhat in this paper. And so we're introducing, to do that, we have to depart from the typical stage games studied in the literature, and we're going to introduce two simple stage games whose repetition does open the door to bad equilibria. These particular stage games do capture some stylized aspects of things like bullying, peer pressure, and bystander complacency. We don't intend them, however, as models of those harmful phenomena. Let me give you a little structural guide to how the paper and talk will work. As I said, this is a paper that involves experiments, but it has two parts. So in the first part, we're going to look at finite repetition of one stage game 1. And there we use a sort of a new methodology, at least for repeated games, that I'll be discussing more soon. In the second part, we look at infinite repetition of stage game 2, which I'll also introduce, using the classic methodology for repeated games. And I'll introduce you to both of the stage games before going into the experiments themselves. And before that, I'll just do a brief overview of the literature given the time constraints. So as I said, there's many experiments on infinitely repeated games. There's a nice survey of Delbo and Frechette. And of course, those are focusing on the sustainability of outcomes better than the stage game Nash. There are fewer experiments on finitely repeated games. Brave, Frechette, and Yüksel does offer a meta-analysis of those and some new data. And even in that context, they find there could be some cooperation, repeated prisoner's dilemma, even finite, but that it unravels after they figure things out. The new methodology, at least for repeated games that I was discussing earlier, relates to the use of suggestions to test self-enforcing natures of strategies. And this has its origins in actually other parts of game theory and was used in certain experiments that are not for repeated games. We think there actually is a great methodology to use for repeated games where the equilibrium set is huge, and by varying the probability of continuation, you get a great treatment and control. So we'll talk about that more later. And of course, this is generally about bad outcomes, and bad outcomes have been discussed in theory for more complicated dynamic games. So of course, there's Ely and Valimaki's bad reputation, which is about the reputation of a long-lived player and how those concerns can actually erase surplus. They then, Elie, Fudenberg, and Levine discuss theoretically when that could happen. Grosskopf and Sarin is an experimental test. And there's also a literature on preventative wars in dynamic games with changing fundamentals. So basically, either due to the position of a country changing stochastically or due to some actions that have been taken or outcomes that occur in the game, that can lead to preventative wars to ensure control of a resource. So again, these are things where the game is dynamic and it's not just about pure repetition. So the outcome doesn't arise from, a folk theorem. So let me now talk about the first stage game. I'll just introduce the stage game to you. It's called the peer pressure game. And a little caveat, I'm going to use very loaded language in the next few slides. Player names and the options that they had were described in completely neutral terms to subjects, as you'll see later. So what is this peer pressure game? Well, let me tell you the players first. There's a group of potential victims, let's call that group V, and the group of bullies B. Okay, so That combination is the set of players. What do? Well, a bully selects a player who's a victim to bully. And a victim decides whether to pay a cost of C dollars. Interpretation, think of paying this cost like conspicuous consumption that gives you no gain otherwise, like you have to buy the trendy pair of shoes in the schoolyard to fit in, or the victim takes some unappealing action like smoking or binge drinking for that
B
purpose.
and B are disjoint?
Yes, they are.
B are disjoint, yes?
Yes, they are. Yeah. So these are different sets of people. The bully's payoff increases by X dollars when they're part of a strict majority of bullies targeting the same victim. So think of bullies as enjoying to bully in concert. And a victim has two potential ways to lose money. They lose L dollars if they're picked by at least some bully, and they lose C dollars if that's what they chose to pay. So you could have one or both or no loss as a victim. Okay, so that's the game. Well, let's just think quickly about the equilibria. So for the victims, clearly C has no benefit. It's strictly dominated in the stage game. And any Nash equilibrium has the bullies coordinating on one victim, nobody pays. So you basically index the Nash equilibria by who's the target. With a chance of repetition, even just a possibility of one repetition, it now becomes easy to construct self-enforcing conventions where many victims pay, even though just one person is ultimately targeted. Now, this peer pressure game has multiple Nash equilibria, and so who bullies target in round 2, if it occurs, can be conditioned on the round 1 outcome, which contrasts, of course, with games with a unique Nash equilibrium outcome, where all you can do is repeat that. So this allows us to say something interesting even about finite repetition. So here's an example of a bad equilibrium. So let's index the players in V. We'll enumerate them 1 through n. Okay, so there's n of victims. Let's suppose, here's how bullies act. Round 1, bullies pick victim 1. In round 2, bullies pick the smallest index victim among those who didn't pay in round 1. If everybody paid, they pick victim n, okay? So if the loss is larger than the cost of paying, and if a second round is likely, victim 1 feels pressure to pay in round 1 to shelter herself in round 2. Once she pays, she's no longer the smallest indexed victim who didn't pay. That now puts pressure on victim 2 to pay. And of course, by iterated reasoning, everybody but n is going to pay in round 1. This is true no matter how large n is. So you could basically have this snowballing effect where everybody pays, despite just one victim who's ultimately targeted. Now, ultimately, this is not a good outcome because people pay. So it's Pareto inferior, of course, to the obvious alternative, which is target victim 1 in round 1, and no matter what, target victim n in round 2. So if that's predetermined, nobody would pay because it has no benefit. If you don't think about the identity of who's getting which payoff and you just anonymize payoff vectors, kind of a sense-based type of comparison, it's also Pareto inferior to any fixed sequence of one-shot Nash equilibria. Okay, so that's an example of a bad convention. Could this happen in real life? It seems there's things like that that are kind of similar because you think of the conspicuous consumption, at least for all victims but n, as reducing your salience to the bully somehow. How you would see this spontaneously arise in a short abstract encounter is harder to see. So before understanding that kind of selection question, we start here with a very basic question. Can a behavior that results in bad outcomes be self-enforcing due to the repetition? So the proposed methodology here draws from that earlier suggestions literature. In neutral terms, suggest a purely non-binding but negative convention for how at least some of the players could choose, and then examine whether people are playing their part in this associated bad equilibrium when it's self-enforcing because the repetition probability is high enough, but not otherwise. So in other words, what we're gonna do here is use that earlier bad equilibrium that I mentioned to you, where what the bullies are doing is pick victim 1 in round 1, and in round 2, pick the lowest index person who didn't pay, and otherwise victim n. And we're gonna keep that bad suggestion constant across treatments while varying the probability of round 2 to see what happens. So that's stage game 1. Stage game 2, again, in purely loaded language, called the bystander game. So this one has 3 players. There's a bully, a bystander, and a helpless victim who has no strategic choices. So they just get a payoff. And all the players start with $M each. What are the options of the bully? The bully could either do nothing, they could harm the bystander, or they can try to steal money from the victim. If the bully tries to steal money, then the bystander is faced with a choice. Do they protect the victim, or are they complacent? If they're complacent, then you get a successful theft. A successful theft reduces the social surplus. The bully is getting $T that they stole. The victim has a larger loss than that. The bystander feels it difficult to witness such a thing and allow it to happen, and they lose some money A2. Okay. Protecting the victim would be costless to everybody, well, except that the bully doesn't get to his theft. And the players, if that happens, the players stay with $M each. Attacking the bystander leads to a loss for the bully, so it's difficult for the bully to attack this bystander. They're not as small as the victim, let's say. And there's a loss, however, for the bystander if he's attacked. That loss from being directly attacked is worse than how bad they feel when they're complacent. Okay. So this is a situation where, if you want to think of a concrete example, think of a school bully who tries to take, or could try to take, a smaller student's lunch money, but a classmate is present. So if he tries to take it, would this classmate, who's a bystander, intervene? Well, the classmate, if we think about the particular game that I modeled for you, the classmate dislikes bullying. I didn't impose any exogenous cost to intervention, like if you step in, you accidentally get punched. So certainly in a one-shot interaction, he intervenes. Notice that the bully finds it costly to retaliate against the bystander. But once you do an infinitely repeated game, this becomes a credible threat. So because there is a unique Nash equilibrium outcome here, it can happen in 2 different ways, but the Nash equilibrium outcome in the stage game is everybody gets $M. So if you finitely repeat this game, you get nothing interesting. You have to infinitely repeat it. And if you infinitely repeat it, retaliating can become a credible threat. And in that case, complacency of the bystander becomes possible because of this endogenous cost of intervention. Now, this is worse in the sense of greater inequality, reduced social surplus. It is better for the bully, and that's why we thought this might potentially occur spontaneously, and we allowed that to potentially happen, as opposed to use a suggestion. So let me go into the details of the finite repetition of the peer pressure game. I'll discuss the experiment itself, the theoretical prediction, and the results. So there's 2 treatments. Round 2, the treatments are either round 2 has a probability 1% or a probability 99%, and those probabilities are constant for the entire session, okay? So we don't switch probabilities on people. A subject at the beginning of a session is either assigned to a low index role, that's our victim from before, or a high index role, that's our bully from before. And they keep this role for all the repeated games, all the matches. There's 30 matches, each of which is a repeated game. So every time we rematch, and in every match, we draw 4 low index players and 3 high index players to construct a 7-person group. So there's multiple 7-person groups in each match, and they each have 4 low index and 3 high index players. So 3 because we want a majority so that the bullies, have a majority from matching somebody else, a strict majority. And we thought having at least a decent number of victims would be interesting to see if you get actually a large number of people playing. And of course, we're sort of flirting here with the people's ability to do iterated reasoning, which is required for them to actually pay and higher indices. So they are divided into these 7-person groups. And if you're a low index player, you get a random number between 1 and 4. And if you're a high index player, you get a random number between 5 and 7. Okay. And then the group plays this peer pressure game. So the particular payoffs are, for a high index, if you selected the same low index as one of your other bullies in your group, you get $5 and 0 otherwise. If you're low index, you start with $13. If you chose to pay the cost, that cost is $2. And if you get selected by a high index player, you lose another $10. Okay, so those are the payoffs. Now, how did this suggestion work? In the beginning of a round, everybody sees the suggestion. that suggestion is just for which low index to pick, and that's displayed to everybody. So this essentially offers a valuable, potentially valuable coordination device for the bullies, because otherwise they have to figure out how they're going to coordinate. So the convention here is just the bad convention from before. Round 1, high index members select index 1. Round 2, high index members select index J, and J is computed to be the smallest index victim who didn't pay in round 1 if it's not empty, and otherwise if that's empty, it's index 4. Then they get group feedback after every round, so this is a standard repeated game where people see what happened. At the end, they're paid for a randomly selected match plus $8 show-up fee. What do we predict? Well, high index players would find a coordination device useful. If they were to act randomly, a quick computation shows that any choice they have leads to at least a 56% chance of 0. Okay? So we suspect they would use the device. For low index players, other than 4, paying in round 1 has the effect of potentially deflecting the bully onto somebody else, right? So if you're altruistic, you might be concerned about that. Under classic theory, and assuming you can do iterated reasoning, you would expect all low index but 4 to pay in the 99% treatment. So when there's a probability of round 2, as opposed to when that probability is negligible. So we picked 99 and 1 to be able to compare essentially something similar to playing it once versus playing it twice, but to keep instruction similar, we have 1% versus 99%, so that there's always this idea of a die roll for the next round. So the hypothesis, to summarize, is that high index members follow the suggestion. There may be some learning in earlier matches because of the iterated reasoning required, but members with an index lower than 3 equal than 3 should pay the cost in round 1 of 99%, and otherwise not in round 2 or in any of the rounds of the 1% treatment, low index members wouldn't pay. So you'd expect outcomes in the 99% treatment to be Pareto inferior. Okay, so what happens? Well, we have 161 subjects. I can tell you that the rate of following the suggestion for the high index players was quite overwhelming. Out of over 3,400 observations, I think there was maybe 50 cases where it wasn't followed. But we're most interested in the low index choices. Do they pay? Okay, so let me show you a bar graph aggregating over round 1 of 99% treatment, aggregating over each set of first 5 matches. So matches 1 to 5, matches 6 to 10, 11 to 15, etc. So remember, there were 30 matches.
Kareen, there is a clarification question.
Yes.
Were they told the entire suggestion at the beginning of the match or at the beginning of each round?
They were in the instructions. They were told exactly how the suggestion works. So they knew in advance how the suggestion works. And yes, so they are aware of exactly how the suggestion is varying dynamically.
Thank you.
Okay, so this is a bar graph here for each of combination of 5 matches, just to put things in a more easily readable format. So red is index 1, blue is index 2, yellow is index 3, purple is index 4. Remember that index 1, 2, 3 should be paying theoretically. We see some learning at the beginning, right? Of course, there's some iterated reasoning involved. By the end, you see 97.5% of indices 1 and 2 pay, 100% of index 3. For whatever reason, you have index 4 making sort of a mistake a little bit. Some of them, 6% around that, still pay nonetheless. Okay. There's 2 possible comparisons to this because they weren't supposed to pay in round 2 and they're not supposed to pay in round 1 of the 1% treatment, nor in round 2 of that, but there was really only one situation where that happened, so I don't have enough data on that. So here's round 2 of the 99% treatment as a contrast. You see, again, there's a little bit of learning at the beginning, but the rate of payment is really very small. Round 1 of the 1% treatment. This shows you that index 1 perhaps treats that round a little bit differently because there is still a probability that they are the main target. And so if they're really risk averse, I suppose you might pay. Okay. Of course, that is not a statistical test, so you could estimate the probability that different indices pay. You can do that using logistic regression. We use robust standard errors clustered by session to account for learning, we drop the first third of all matches throughout this paper as sort of a rule. And you see that the estimated payment probabilities in round 1 are really high for 1 to 3, close to 1, not quite 1, but close to 1, and at least 90 points higher than in round 2 or in round 1. Okay, so there's a pretty dramatic difference, and it is significant. You see that player 4 does sometimes mistakenly pay as well. And of course, depending on risk aversion, maybe you would pay as index 1 in round 1. Okay, so that's a fairly overwhelming difference that we find. And of course, the payoffs go down. You see statistical difference in the round 1 payoffs. They are worse. But for interest of time, I'll move on to the infinite repetition of the bystander game. Okay, so again, I'll talk about the experiment, the theoretical predictions, and the results. Okay, so we had, again, 2 treatments. Now that we're in an infinite repetition setting, that basically means that every round at the end of the round, subjects are told based on some kind of simulated die roll, whether it continues to another round or not. So it could go on, theoretically forever. Delta was 10% or 75% in our treatments. And again, the probability was held fixed for the entire session. Okay, so at the beginning of a session, a subject is assigned to a role, either player 1, corresponding to the bully, or player 2, corresponding to the bystander, or player 3, who is the victim. And remember, player 3 has no strategic choices. Player 1 acts first, and player 2 acts if asked by the bully to make a request for essentially theft, but that's not how it's phrased. So they keep the role for all 15 matches or repeated games here. Because the games could potentially last a long time, we had to do less matches to keep this reasonable. At the start of a match, what happens in every match, we rematch people randomly, and we divide them into 3-person groups. So we draw 1 player 1, 1 player 2, and 1 player 3 into each group. And then they play the bystander game. So here the payoffs are in experimental points, and they get feedback for what happens after every round. So here's how the options are phrased. Doing nothing is baseline, and that means everybody gets 100 experimental points. Harming the bystander is deduct from 2. That means player 1 at a cost of 2 experimental points reduces player 2 by 50 experimental points. The theft is a transfer request from 3 to 1. So if the transfer request is denied by player 2, that's transfer from 3 to 1/no. Again, everybody gets 100. But if the bystander says yes, player 2 says yes, player 1 gets 40 points at the expense of 50 points for player 3. Player 2 loses 10 points. So the idea here is there is some evidence that bystanders feel guilt from being complacent. In this kind of session, in this kind of experimental setting here, a player might dislike inequality, or they may feel guilty to have done that to player 3. So those are sort of psychological things that they could feel potentially, but by reducing the payoff by 10 points, we made sure there is a tangible component, even if there wouldn't have been otherwise. So the player 2 here doesn't like saying yes.
Kareen?
Yes.
Let me just tell you that you have 7 minutes to go.
I do? Okay. So there.
My mistake? Sorry.
Okay.
I'm sorry, I made a mistake. Sorry.
Okay, that's what I thought.
Sorry about it.
Okay, so they are paid for a randomly selected match at the end, and of course there's also an $8 show. So the theoretical prediction for delta equal 10% is pretty simple. Everybody gets 100 experimental points because that is the unique subgame perfect equilibrium outcome. It's actually not very hard to see at all, because even if player 1 would to impose the harshest possible punishment on player 2 by deducting him forever after he says no, and by the way, that would not be incentive compatible for player 1, but if he were to do it, even if he were, deviating to no would actually be better for player 2 if delta is 10%. On the other hand, the payoff set is much larger when delta is 75%. In fact, player 1 can achieve a successful transfer in every single round. The strategies are pretty simple. Maybe there's another way to do this, but here's a simple one. Player 1 chooses transfer from 3 to 1 all the time, except If player 2 ever says no when they were supposed to say yes according to the strategy below this, then they deduct them once. Okay, so there's a single one-time punishment after saying no. What does player 2 do? Player 2 starts from the position of saying yes all the time, but they switch to no forever if player 1 ever fails to deduct him right after saying no. Okay, so this, if delta is 75% or even smaller, would sustain successful transfers in every single round.
Mm-hmm.
So that's just the argument. Okay, so putting it together, you would expect bystander complacency and successful transfers to be rare when delta is low. They could be significantly more frequent when delta is large. So you'd expect more inequality and lower total surplus when delta is large. Okay, so here we had 225 subjects. There was at least 500 or 600 super games played. And these super games could be quite large. So in the sense that in the delta equals 75% treatment, our longest super game ended up being 19 rounds. Okay? That can get a lot of pollution from dynamic considerations. So what's standard in the literature is often to compare what happens in round 1, where you sort of freshly matched people. So that offers the cleanest comparison between the treatments. So I'll start by doing that. And what we'll do is have a match-by-match look at what player 2 does in round 1 if they get a transfer request in round 1. So this is the complacency rate. And we'll compare that in delta equal 10% to 75%. Okay, so this is the percent of yes to transfer requests in round 1. So the blue is the 10% continuation probability. You see there's a little bit of learning here, but for the most part, that's pretty small. The red is the 75% continuation probability. And that is sort of, once this learning is dropped, is hovering around 40%. Okay, so you see it looks a bit different. If we actually estimate that rate, again, dropping the first third of matches, using robust, cluster robust standard errors, what you would see is that the complacency rate is about 42% in the 75 treatment and about 7% in the 10% treatment, and these are significantly different from each other. Of course, how important that complacency rate is hinges on how many transfer requests are actually made. So we'll go into that more in a moment. I can tell you around 2/3 of requests approximately are transfer requests. And so if you think about all round one outcomes, in 10% you get less than 5% of successful transfers, and in 75% that's at least 20 percentage points higher. And the impact on payoffs is similar to what you would expect. There's a decrease in total surplus and a clear increase in inequality. One thing you see is that in 10% you get more deductions and a small number of successful transfers, so those are not exactly payoffs of 100. And we weren't entirely sure why, but it could be that people misperceive the continuation probability. It could be that some people are kind of influenceable, and if you ask them to do something, they do it. It could be that if there is a second round, they're worried that they're going to be deducted just for purely intention-based reasons. So there could be potentially some ORP type reasons for that. So let me take a closer look at what player 1 is doing. So dropping the first third of matches means we're looking at matches 6 to 15. So the theory, interestingly, doesn't make a prediction about whether baseline or transfer should happen. In the 10% case, the latter is weakly dominant. There are some SPEs in the 75% that could involve using baseline. So maybe you have to start with baseline before you can ask for a transfer request. And we see that there's a small difference in the round 1 baselines, so going from 24% and 10%, increasing to 75%, increasing it to 33% in the 75% treatment. So that is a small difference that we find. It could have something to do with those kind of funny equilibria, but there's actually a curious gender difference we find that I'll show you on the next slide that may account for that. But having said that, what we see is that nearly 70% of requests in delta equal 10% are transfers. Of course, these are almost always denied. And in 75%, that is slightly lower, but very similar, 64.5%. You don't see any significant use of deductions. These are not statistically significant. it is a bit curious that some more people seem to do deductions in round 1 of 10%, almost like an opportunity to just not be nice. I'm not really sure why. But what you see is that for every treatment, it is more likely than not that player requests a transfer, because these are not just different from 0, they're even significantly larger than 1/2. So deduct in 10% is a dominated action, so that's particularly surprising. Again, because of funny SPEs that you could get, deduct is not dominated when delta equals 75%. You could actually start an SPE with deduct. It's not something we would expect to see. However, you might expect to see deductions in the second round, right? So now if you want to think about histories that are comparable and what people do, we thought it was interesting to consider a situation where in round 1, the player made a transfer request. And then think about what the player 2 did. Did they say yes or did they say no? And as a result, conditioning on the yes or the no, how player 1 responded in round 2. So let's look at round 2 after yes. There's literally nobody. That's why there's no standard error here. There is not a single person who deducted after a yes in the 75% treatment. I don't have enough data in the 10% treatment to discuss this. But after a yes in the 75% treatment, not a single person deducted. Most people just requested a transfer request again. After a no, you get a very different story. You get a significant use of deductions, more so in the 75% treatment, where you would expect that's sort of a punitive action, potentially to influence behavior later. In the 10% treatment, you also see some deductions. And it's interesting that some of the repeated games literature finds that there's more effects of other regarding preferences, like intention-based preferences, in low delta situations. So this may just be sort of an intentions-based reaction. And we're not exactly sure where that comes from. But it was quite interesting that nobody says deduct after yes, but it is used quite significantly after no. And I did hint towards a gender difference that I want to point to now, because actually some of what you see here is hiding a lot of heterogeneity. Okay. So here's a breakdown by gender. In round 1, delta equal 10%. You see men and women act really similarly. I mean, these are not just statistically different, but they look really similar, okay? So it's kind of surprising what happens when you move to delta equals 75%, given the similarity in 10%. Men switch from baseline towards transfer a little bit, okay? Women switch from transfer towards baseline. So it seems that when the request is actually enforceable, women tend to make it less, which we found somewhat surprising. Perhaps it's a discomfort with actually carrying that implication that you might enforce it. We weren't really sure. And of course, nobody knows if the other person that they're facing is a man or a woman. Now, on top of that, if you think about how they're choosing in 75%, men are 4 times more likely to choose transfer than baseline. Women are kind of split half-half. Now, let me point out that men and women act the same in the bystander role. There's no statistical difference between how they act. There's no statistical difference in how they act in round 2 after having received received a yes from player 2. After having received a no, however, there's a very stark difference in behavior. In fact, the behaviors are almost reversed. In both cases, though, nobody says really, or few people ask for baseline. The question is, do they deduct player 2 after having said no, or do they transfer request again? For men, it's 73% chance of deducting player 2 after a no, and only a 23% chance of saying another transfer request. For women, it is completely reversed. 16% chance of deduction, not even significant, and a 76% of a transfer request again. So we found that very surprising, might be worth further study, because we're not exactly sure where that's coming from. It would be interesting to study that further. So just to wrap up some takeaways, The experimental literature on repeated games has focused on a relatively small set of classic and important stage games, but we do find it worthwhile to widen the scope of the games studied. And this, of course, opens the door to bad equilibria. And we unfortunately established that those are sustainable in the lab, so they could also potentially be sustainable in the real world. If we start exploring equilibrium sets, which we think is important, that does mean using the full force of folk theorems, not just Nash reversion. And it means that equilibria can be very, very large. So how do we study a question of interest in that case? Well, we think our proposed methodology is useful for that. It offers a way to trim the equilibrium set. You can test a particular question and you have this perfect treatment and control by varying the continuation probability. And you can see whether a behavior arises because the continuation probability is high, but that the suggestion, which you're keeping constant in both cases, doesn't lead to the bad equilibrium when the probability is low. And as a methodological benefit, that means your instructions are always the same. You're just varying the delta. So that's the only thing that changes. And of course, as a final note, we've talked a lot about words that have to do with bullying. We don't intend to model bullying per se through our games, although they may capture some stylized aspects of that. We do think that repetition could potentially play a role in that harmful phenomenon. And in fact, there are some formal definitions that basically say that you're a victim of bullying if you've been subject to repeated situations where you've been exposed to negative behaviors. And there is quite a bit of literature on that public health issue to say that there are very deleterious effects on that. So continued research on that is, obviously quite an important thing. And that is all I have to say. Thank you all. It's great to have this venue to see you all, and stay well.
So we have time for panelists to ask questions if they do have.
I have a very trivial question. Do you think it's worthwhile to do an anonymous questionnaire asking them afterwards why they behaved the way they did?
Yes, so we actually do have an exit survey, and that exit survey involved some demographic questions. Are they male, female, etc.? But I think we also asked some questions to describe their choices, and we did get some interesting responses, things you would expect, and others where we thought that provides an interesting hypothesis. So for instance, some people mentioned, I offered as player one, as the player one, I would offer first baseline so that they would accept my request in the second round. And then we actually looked in the data to see, does that in fact lead to a higher probability of player two saying yes? And actually, in fact, that was the reverse, that when people asked or started the round by requesting baseline and then asking for a transfer request, they had a lower probability of getting a yes out of the bystander. So that was, informative in some ways. Not all of it is included in the paper, though.
Thank you.
Somebody asked, have you also checked how exactly the participants switch from round one to round two actions? Like you have shown the probabilities of choosing either option, but have you tracked how many of, example, like a woman who played baseline in round one, then switched to transfer in round two? Anything interesting there?
So yes, conditional on a transfer request in round one, but we haven't done all the possibilities because, as you imagine, the data is quite large. And there's many questions you could study. So what we did do is what I showed you, which is following a transfer request. How do you do that? And I don't think we looked at people who start with baseline and what they do in the next round, but we did see that when that happens, the probability of a yes actually goes down.
Any other questions?
Yeah, Kareen. So I was wondering, this is Naveen. I was wondering if, in some sense, your first experiment in particular might be overly pessimistic because you're very explicitly sort of making a bad equilibrium salient through the instructions.
Yes.
And one might instead be interested in sort of seeing from the folk theorem's perspective, one might be interested in sort of seeing which of these equilibria spontaneously emerge.
Sure.
And I was wondering if you could comment on that.
So there's many different possible equilibria there. Any sequence of equilibria would be this target and then a next target, but the rule for how you go from one to the other also is incorporated into the equilibrium. I don't have any good sense of what would happen if we didn't have a suggestion. We had a good sense because the bad equilibrium is better for the bully, and they have an incentive then to sort of use that aggressively, that could potentially arise spontaneously, and of course did. In the bystander game and the peer pressure game, it's not obvious, how they would learn to settle in a short interaction. So there we thought the question of interest is, suppose you sort of construct this culture of peer pressure, or attempt to construct a culture of peer pressure, is that actually becoming entrenched? And it doesn't become entrenched with the 1%, but it becomes entrenched with the 99%, because it's really, what's really interesting here is how the player ones respond, the low index respond.
But in the 1% case, it's not an equilibrium, correct?
It is not the bad equilibrium is not an equilibrium, which is exactly why we think it's interesting to see if it happens, right? So what we're suggesting is just a behavior, a coordination device for bullies. We're not telling the players the low index what to do. So it's really just the bullies, not the victims, who are getting a suggestion. And the bullies are getting a coordination device. It is in their interest for them to pick it up, but whether the payment, the peer pressure sort of payment of the low index players, the victims, is what we're interested in. And so in the 99% case, all these victims are paying for, just to avoid this possibility of bullying that doesn't get picked up in the 1% case. And that's exactly what we wanted to test. So you don't get the associated equilibrium. We're not suggesting an entire equilibrium. We're just suggesting an action or a coordination device for bullies, and seeing whether that constructs this sort of peer pressure culture. And it doesn't when it's not in equilibrium. So that's exactly what we were interested in testing.
Any other question? Kareen, can you tell me how can I avoid bullies as a result of you?
More research is needed.
Okay. Thank you.
I think Rani had a question. I saw a hand raised. I don't know, Rani, if your question was answered.
I didn't see.
You can unmute yourself.
Yeah.
It was answered. Okay.
Yes, Naveen basically asked that question.
Okay, we are almost on time. Thank you so much, Kareen. It was a pleasure. And in half an hour, we resume with Bob Aumann.